Hi, this is Miss Litton, and this is a lunch period review with my wonderful, excellent AP biologists and a few honor students doing a lovely lab about enzymes that any of these kids right here could help you with. Say hi.
Hi.
All right. Okay, so on this one, I just thought I'd jump right to what would be maybe a hard problem for some of you to do. So if you're presented with data like this, a black bunny crossed with a white bunny, and they have 12 baby bunnies. Okay, now I made this one an easy one to figure out, okay, just so you could practice doing it. 2 were black, 9 were gray, and 1 was white, okay? What type of inheritance do you think this is? And based on that inheritance, is this data acceptable? Or do we think something else is coming into play? So first of all, let's talk about what kind of inheritance do we think this is? Tell me. Incomplete dominance, right? Because it looks like there's blending. It's not really. It's just that both the white color is getting laid down and the black color, so it appears like blending to us, but it is really incomplete dominance. So if we did a cross like this and it was incomplete dominance, if you had a black bunny, well, how could we set that Punnett square up? Here, let me go on a whole new page. Okay, how could we set that Punnett square up if we say it's incomplete dominance? Because you would be able to do this. You'd be able to figure it out. Incomplete dominance. What do we want to do? Color, C. Okay. Or, so you could have C1 and C1 equals black, right? What else would you do? C1 and C2 equals what? Gray. And then C2 and C2 equals what? White. Okay, so you would want to be able to explain how you were setting that up. And I said a black bunny, so that's a C1 and a C1 crossed with a white bunny, which is a C2 and a C2. Okay, is that right? Okay, so now if you did it like that, then what would all of them be? They would all be gray. Okay? So is our data unusual for that? Because we had some still turn out black and some still turn up what? White, right? Okay? So let's go and try, let me go back here. So you know what I really should have crossed. Can we do a different cross? A simpler one? Let me cross it's okay, we can keep doing this one. It'll be good for us. Okay, so we expected all of them to be gray, and we got some black, 9 gray, and 1 were white. So let's do, remember, our observed minus our expected, right? So what were let's see, black, gray, white. What would you expect for how many black ones you would have? 0, how many gray? 12, because we had 12 options. How many white? 0. Okay, and how many blacks did we get? 2 were black. How many? 9 and 1. Okay, so now we need to do our observed minus our expected squared, right? So observed minus 2 minus 0 is what? 2. And then, right, and then we're going to square that, 2 squared, sorry, it's over what we expected, which would be 0, yes. And then here, 9 minus 12 is what? This is going to be a bad one. There's no way I can fix this one from here. What is this one going to be? 3 squared over what we expected would be 12. And then here it would be 1 squared over 0. It's not going to work because we got that. Do you understand what I was trying to set up? I should have crossed a black bunny and a gray bunny or something like that. That's what I should have done, but I didn't. I'm so sorry. I just came up with it at the end. So once you do this, okay, then you would add up, right, those 3 values, and then we would look on our chart, and we would look to see. Now, in this case, how many degrees of freedom did we have? How many degrees of freedom? We had 2 degrees of freedom because how many phenotypes did we have? 3. So then we would look up our value right here, okay? And we have 3 degrees of freedom, and if it's, 2 degrees of freedom. And so we would be, you're looking between these 2 choices. Now, what of these two choices is okay for us? Do you remember? If our number, notice, look here, 5% of the time it's 5.99, and 1% it's 9.32. So what happened to that number? It got what? Bigger. So if we're expecting it to be okay, acceptable, remember our cutoff point is 5%. So as long as your number was smaller than 5.99, then that would be acceptable. As long as your number was smaller than 5.99, then it would be acceptable. And I would give you a better one to do on your quiz, okay? We could try, that one was an incomplete dominance one, where you had 3 different phenotypes. But if I did tall versus short, you would have 2 different phenotypes if we did one similar. Okay, if I crossed a tall pea plant with a short pea plant, okay, and let's say I had 100 pea plants that came out from that. Okay, and if, let's say, 60 were tall and 40 were short, is this okay? How would we go about setting this one up? What do you think the genotypes of the parents are? You say big T what? Big T, little t, and this one is for sure going to be what? Little t, little t. Now, why did you say it was a heterozygous tall plant? Because you got a whole bunch of what? Short. So if we did this Punnett square, we have big T, little t, crossed with little t, right? We would expect 50% of them to be tall and 50% of them to be short, yes? Okay, so this is what we got. So this was our observed. Our expected, if we're doing a cross and we have 100 offspring, we would expect 50 tall and we would expect what? 50 short. Okay, so now we're going to take our observed minus our expected. So here, 60 minus 50 is what? 10. So now we're going to do 10 squared over how many? 50, right? Because you do it over what's expected. And then again here, also, how many squared? 10 squared over 50. So now you have, what's 10 times 10? 100 divided by 50 is 2. So this value is 2, and this one's going to be 2. So when we do our sum of that, what's 2 plus 2? 4. Are we going to accept this number? You want me to go back to the chart, or do you remember the number? Look at the number right here, okay, on our chart. Okay, now, in this case, we're not how many degrees of freedom are we? 1. So 1 degree of freedom is, what's the number that we have to look out for? 3.84. What was our number? 4. Is this data acceptable? No, it's not. Okay, because it would happen less than 5% of the time. Remember, we went from 3 phenotypes down to how many? 2 phenotypes. Okay, so when we added that up, 10, remember 10 squared is 100. 100 divided by 50 is what? 2. So we had 2 plus 2 was 4, right? So when we had a chi-square value of 4, that is unacceptable. Okay, because it would happen between 5 and 1% of the time that you would, by chance, get that kind of deviation. So we would have to say there must be something else. Maybe the sample size was too small. Maybe there's another form of inheritance in there. Maybe epistasis is taking place. Now check with the person next to you and make sure they understand the process that we go through and whether we accept it or reject it. Okay, next, I wanted to you want me to go through it? Do you need any more help on that one? Are you good? Okay, so let's take a look at this. Which of these pedigrees works best as a dominant trait? We can just do it. Did you want to click in? I don't think I have a list open. Let's just keep going. Talk it over with your bio buddy. Which of these would work as a dominant trait? Okay, and in these scenarios, you'll have scratch paper for your quiz. And so what I would do is I would be writing it down on the scratch paper and seeing each one if it works. So let's go through and do this. If this were a dominant trait, okay, so in order to have the disease, I would have that capital letter, whatever it is you want it to be. So this would be at least one big A. Do you agree? Okay, and then this would be what? 2 little a's because they don't have the trait. Okay. Now this individual, you know, is going to get 1 little a because that's all the dad has to give, right? So I know I'm going to get 1 little a, and regardless of what this trait is, could they give them the big A? Yes. So would that work as a dominant trait? Yes. Okay. So yes, this would work as a dominant trait. Would this one work as a dominant trait? No. Why not? Dominant traits don't what? Skip generations. So these individuals right here would have to be little a, little a. Now, if it was without the bottom part down here, would this work? If I didn't have them having these children, would this work right here? If all I gave you is this much right here, would that work as a dominant trait? Well, this could be little a, and this could be big A, little a, right? So it could work as a dominant trait just if I gave you this much information. If this is all the information I gave you in the red square, yeah, that could work as a dominant trait. But I told you, okay, I gave you this bottom part down here, which showed you that the trait was popping back up again. So that means it can't because we know neither one of these parents had the disease. Do you see the difference? Okay, so no, this will not work as a dominant trait. Will this one work as a dominant trait? Super no, right? Because these parents don't have the disease and they have a child that does. So how could they pass that on? Okay, so this will not work as a dominant trait. Okay, check the person next to you, make sure they understand. Clarifying questions on that? Anything you want to ask me? Okay, so let's do another one. Which of these pedigrees would work for a recessive trait? Which of these pedigrees would work for a recessive trait? Okay, let's start with this one. Now I'm going to label it a little bit differently. When they have the trait, what am I going to say right here? Little a, okay? What would this one be? Okay, this one doesn't have the disease, so they have at least what? 1 big A. Do we know what their second letter is? No, but could it be a little a? Yeah, sure, it could be a little a. So as a result, they could both give it to their daughter, right? So would this work for a recessive trait? Yes. Okay, anybody need me to clarify that one? Okay, let's go on to the next one. This one right here. This individual would be what? Little a, this one? Big A, do I know what the second letter is? No, I don't. I have no evidence of what the second letter is. But I know that this individual right here would get a what? Little a. Now, do I know what this other letter is right here? If we're doing this on a recessive trait, what is it? Yeah, it's a big A, okay? And now, what is this one right here? At least 1 big A. Could their second letter be a little a? Yes. And so if they both gave a little a, then they could have this boy who has the disease. This one, I don't care. One of them gave, they could have 2 big A's, they could have, 1 big A, 1 little a, it doesn't matter. Yes?
Can you just see that it skipped a generation and know that it's a recessive?
You could, but it might ask you, I would probably go off of that, but you want to make sure you understand why in case you have to support your reasoning. Yes?
For the sake of this problem, the square circle doesn't matter, but it's just like the parents.
If it's autosomal, it does not matter.
Right, what I'm saying is like.
If it's sex-linked, it does. For the sake of this problem, when I just said recessive trait,
Yeah.
doesn't matter at all. Doesn't matter at all. Yes?
Would it matter whether you got white was recessive or black was recessive?
No, it's because I asked you here, recessive trait. So the trait I'm following, I'm saying in this scenario it's recessive.
So you're just assuming that one. Because like in the previous problem, you said that black was dominant and they would have.
No. In the last question, what I asked you is, if this trait was a dominant trait, or wherever that is. Yeah, I asked you specifically if the trait was dominant. So here I'm telling you the trait I'm analyzing here that's dark, would it work for a dominant trait? In this one I'm saying, what if this is a recessive trait? So if you were a geneticist, somebody could come to you with an inheritance pattern and you could differentiate, well, this would work with a dominant or a recessive trait. Well, this would only work with a recessive trait. You see what I'm saying? Okay, now let's do this one. Would this one work with a recessive trait? What would the genotypes be of the parents? Yeah, they would both have to be heterozygotes and they would both give the 2 little a's. You all right with that? Okay, now, which of these would work with sex-linked traits? Which of these would work with sex-linked traits? Okay, what's the dad's genotype? What's the dad's genotype? We're not little a. This is sex-linked trait. You got to give me what? X's and Y's. So the dad would be XY. Start with that. Mom is XX and daughter is XX. Do you agree with that? Now we have to put the letters on. All of the sex-linked traits I would give you are all going to be what? Recessive. So in order for mom to have this disease, what does she have to have? 2 little a's. Yes? Dad does not have the disease, so what does he have? He has a big A. Yes? Because he doesn't have the disease. But this daughter, in order for her to have the disease, she would have to have 2 little a's. No problem getting it from mom, but is she able to get it from the dad? No. So will this work for sex-linked? No, it will not. Because when a daughter has a sex-linked disease, so too will her father. Right? The father is going to give her the second bad one because we're assuming for our sex-linked diseases that they are all recessive. Yes? Okay? So now let's look at this one. Okay? So again, start off, you've got girl, you've got a boy, you've got a girl, boy, you've got a boy, and you've got a girl. Okay? So if the dad has the disease, he has a what? Little a. And you know the mom, she has at least 1 big A. Do we know what her second letter is? Do we know that? Okay, now they formed a daughter, so we know, okay, he gave her a what? Little a. And she doesn't have the disease, so mom had to have given her a big A. Okay, this man doesn't have the disease, so he has a big A because he doesn't have the disease, right? Okay, this son they had has the disease. Could he get it from his mother? Yes. Mom could give him that, and because it's a boy, dad gave him the Y, right? This daughter does not have the disease. Now, mom could give her either one of these, but we know dad will always give her a good, yeah, he's always given her, so we don't care which of these, but she could not have the disease because dad will always give her a good copy of the gene. So will this work for sex-linked? Yes, this one works. Okay, this one works. Okay, this scenario. Dad doesn't, this is dad, mom, son. Okay, so dad doesn't have the disease, so he's a big A. Mom, does she have the disease? No. So she has a big A, but you're assuming she is a carrier. because her son got the Y from the dad, and is it possible she could be a carrier for that disease? Yes. So yes, that one will also work for sex-linked diseases. Yes.
So for the sake of sex-linked diseases, the Y doesn't really matter with the Y. But Y doesn't even give anything. It just assumes there was X now.
For the sex-linked diseases, there are traits on there, so I don't want to tell you the Y doesn't matter, but for the purposes of us, it doesn't matter. Yeah. For the purposes of this, it doesn't matter. Okay, so even though I royally screwed up that first problem by not thinking that through for you, do you understand how to predict and then do a chi-square test and see if it's acceptable or not? Okay? And then do you understand how to look at these and tell whether or not that's acceptable? Okay? Then you need to be able to like look at things and say, what percentage, like to be able to do a Punnett square and tell me like what percentage of them do you think will have the disease or be a carrier for it, those types of things. You need to make sure you understand when a chromosome is flipped. What do we call that if due to crossing over a chromosome gets flipped? That's an, do you remember? Inversion. If you lose or gain a chromosome, do you remember how we talked about duplications and deletions, right? So review what those are called, those definitions. Do you know Mendel's 3 laws?
Yes.
Law of dominance, law of segregation, law of independent assortment. Okay, and then the best way to be ready for this quiz is doing what? Practice problems. And so you know, because I want to give you a chance to see how well you work with your bio buddy, I'm going to let you take your quiz with your testing buddy tomorrow so you can practice how you're going to do it on the real world. Okay? So you are the first to know that. Okay? All right? Questions or concerns? I am here 7th period. If you want to come by, I am here. Okay? I am here 7th period.